Hello, IITians. I hope you all are doing wonderfully. Your host and host Noman, a data engineer at Oracle team, is back to welcome you another exciting Codecrafter session. At Codecrafter, we are dedicated to empowering you with the coding skills and the knowledge needed to thrive in the digital age. We are excited to continue our AI/ML series, delving deeper into the transformative world of artificial intelligence and machine learning. Tonight, we are shining a spotlight on large language model, a technology that pushing the boundaries of what machine can understand and communicate. To guide us through this fascinating landscape, we have the privilege of welcoming our two AI luminary, Luis Serrano. Luis is not only the founder and the CEO of Serrano Academy, but also a celebrated AI scientist and engaging YouTuber, and the author of the acclaimed Grokking Machine Learning. His impressive career, including the key roles Apple, Audacity, Google, and Zapata AI, highlighting his passion for both AI innovations and education. And as a head of developer relation at Coher, he is actively working to make AI more accessible to everyone. So without further ado, let's give a resounding Codecrafter welcome to Luis Serrano. Luis, we are all ears. Take it away.
Thank you so much, Maud, for that very nice introduction. It's an honor to be here at IIT. Great school, great program, the data science program, and Codecrafters is a wonderful group. So I'm very thankful to you and see it for the invitation, and very excited to see everybody joining us here and on a Sunday night. So thank you very much. It's an honor. So let me start sharing my screen. And I believe time-wise, we have about an hour, but it could be more, an hour to 2 hours, roughly.
Yeah. We have it.
Okay, just tell me when, when I should when I should stop
Yeah,
talking.
yeah. Cool.
But this is more of conversation, so I really want to. I want to have more of a chat. Wait, let me figure this out 1 second. So I have the chat in front of me, which means people can ask any questions. I believe we're also in YouTube Live. So yeah, I'd love to make this more of a conversation rather than a monologue. So please shoot your questions in the meeting chat, or even just loud, like just want to talk, by all means. All right, so I start. So I'll tell you about large language models, which are a huge thing now. And for me, it's been interesting because I started AI when the big boom of AI about 10 years ago, which was discriminative, and now there's another big boom, which is generative. So it's really nice to see both of them. Discriminative is basically the one that asks questions, right? So I can ask it a question about an image, and I say, well, is this an elephant? And the computer will say, yes, it is. Yes, no questions, right? Like a spam. Is this email spam, or is the sentence happy or sad or something like that? Yes or no. Is answering questions, and our minds were blown when that happened. Now they're even more blown because you can say draw it, draw the elephant, and it goes, okay, here it is, right? This is for images. And for text, it's the same thing. 10 years ago, we're mind blown when it would ask if the sentence is happy, and it would be like, yes, this sentence is happy. Sentiment analysis. Now what it does is it generates a sentence, right? So I say write a happy sentence, and it just kind of writes it. Or I can say even something harder, right? Like 10 years ago, it'd say, does this sound like Shakespeare? And I would say, yeah, it kind of sounds like Shakespeare. And I would say, write something that sounds like Shakespeare and make it about elephants, and it will write something that's exactly what we ask it for. So this is really fascinating. I think when LLMs came out, and when I started interacting with ChatGPT and a bunch of other ones, the Cohere one where I worked until not long ago, these models are amazing. I mean, these models are just something else. Like the fact that they can talk like a human, it really blew my mind. Even though I'd seen all these advances happening in real time, it's still a step that blew my mind. And today I will tell you basically, how I understand these LLMs, and what is it that we still have carried from before, and what is it that is new. Obviously the new thing is, we have a lot more computing power, bigger computings, more data, but there's a very special step that's called attention, that is really what made everything work. So basically, what is a transformer? So I like to see a transformer like a transformer that generate text. But this is what actually blew my mind the most when I started looking at how things like ChatGPT operate. These things generate text one word at a time. One word at a time. Which is weird because we don't talk like that, right? Like when we're humans, we kind of formulate an entire thought and then we adorn it with words. But this is really literally just telling us the next word. So for example, if I say, hello, how are you? Then it really just says doing is probably the next word. How are you doing? Or how are you good? Or how are you? It's just one word. And then it generates the next word. So if I say, for example, write a story, it doesn't start thinking of the story. It only says, what's the next word after write a story? Well, it's probably once. That's the next word. That's as far as I get. And then how do you make it write paragraphs? You say, well, now write a story once. What's the next word? And it goes, upon, and so on, right? And then you say, write a story once upon, and it goes, ah. And it does it really fast. So it looks like it's talking, but it's generating one word at a time. And so that's old, right? Like we've seen things that generate one word at a time from a long time ago. Any ideas of where you've seen something that like could generate one word at a time that's not new at all? By the way, somebody in the text asking for the YouTube link, so if you can be kindly add it. And Arindol says autocomplete, correct? You're correct. Autocomplete is pretty much the same concept as ChatGPT, right? It generates one word at a time. I use WhatsApp a lot, or texting messages or something. And if you say, hello, how are? Well, there's your next word. It says you, your, and things. That's one word at a time, right? And how does it work? It uses a neural network. So I know everybody here is a data scientist student, so I won't get into the details of neural networks. If you want, by the end, we can talk about neural networks as much as you want. But I'm kind of gonna, for this talk, take neural networks as a given. But basically, neural networks are something that if you give it a lot of data, it starts finding the right correlations and be able to mimic the data. So like if you give it a lot of sentences, it guesses what the next word is. So it will know, for example, that if you say hello, how are, then it guesses that the next word could be you, or it could be your, or something like that. Now, I don't know if anybody has tried this. Don't try it. But if you try it, sending a text message by typing the middle word in every that WhatsApp suggests to you, and just continuing typing that, and then send it to your friends and see how they do. I lost a lot of friends by sending this nonsensical messages because it makes no sense, right? It makes absolutely no sense. I did this one that says, hello, how are, and I started pressing the middle button, or hello, how are you? Feeling this weekend, your kind wishes for a wonderful weekend with your kindness and happiness for your family, love you, and your kindness. Because it's not designed to talk. It's designed to autocomplete, right? Yeah, this is great test subjects. Yes, absolutely. But it does make sense, right? Like it does make sense in a short sense. In a short, for example, if you look at every 3 or 4 words, they make sense. Hello, how are you feeling? And happiness for your, like it remembers a little bit. It's like a person with not a lot of memory that remembers the last 3 or 4 words. And then it can talk like that. But what's special about transformers is that when it's building the last word, kindness, it's thinking of all the other ones. It's capturing every single thing is said before, which is not easy, right? But one thing of attention is that it manages to remember everything. So even though it's building one word at a time, you're in the middle of a long story, and the next word is, I don't know, werewolf. But that word has read the entire thing to come up with that word. So it still doesn't make sense to me why it talks so well, but at the very least, it looks at everything behind. So that's really the thing of transformers, which was attention. But basically with a basic neural network like the one that WhatsApp uses to autocomplete, we can't talk. So we need something more advanced, and this is where the transformer architecture comes into play. This looks like a messy thing, but in reality, this is the neural network. This is the plain sort of neural network that WhatsApp uses. WhatsApp much bigger, but it's a neural network that guesses the next word. And the key for everything is here. It's a multi-head attention. So today I'll tell you how I see attention. There's also something very important underneath that is embedding. Okay. I'm going to answer questions on the real time if I see them. So Ronak is asking if the transformer has any kind of data on it. Yes, it is trained with a lot of data. It is trained with the entire internet, basically. I'll get into that. But I'll get into this thing over here. Embeddings is very important. But attention is really what pushed the limit, like what really made them talk. So let me give you an idea of how I see the structure of transformers. That last image in the paper confuses me. I like to see it like this. You have an input, which is write a story. Then you go through something called tokenization. Then you go through something called embedding, which I'll make a big deal of it. Then you go through something called positional encoding, that it makes sure that if you rearrange the words, you get something different. Because I could say something, a bunch of words, and I reorder them and change the meaning. So positional encoding takes care of that. And then we get to the meat of it, the important part, which is series of transformer blocks, which is the feed forward, which is the neural network that guesses the next word, and attention, which is the step that pushed it. And then you finally get into a Softmax, which basically is the final output that gives you the word one. So all this stuff happens to output one word. Okay. Today we can get into, I think we can get through all of these. Depending on time-wise, I'll start with the important ones, and then we'll get from there. So the important ones are the feed forward and the attention. But let me first tell you about embeddings. Embeddings, I know I sold the attention one as the most important one, but embeddings is really, I would say, the most important element in large language models, and I would say in machine learning, because it's really where the rubber meets the road. It's really where the translation is happening. Because you see, humans, we speak in sentences and words, and computers don't use sentences and words. They use numbers, right? And no matter what you do, the first step has to be turning your words into numbers. And that's what embedding does. And so the better an embedding is, the better that everything will be. You know, if somebody comes up with a better embedding tomorrow, rest assured, all the models are going to be better, because the better translation we do to the computer, the better it can do. And so, for example, I've seen that, 10 years ago, some problems were very hard, like classification, sentiment analysis, finding if an email was spam, if a sentence was, it was hard, and you needed a lot of data for that. Now, with much better embeddings, it becomes a simpler problem, because you're given the computer better numbers to work with. So embeddings are very important. And how do I see embeddings? I like to see them visually. So here is a quiz. So I have a quiz for you. And the quiz is, I have all these words, and the question is, where would you put the word apple? So as you can see, I have some sports here, soccer, basketball, baseball. I have some houses and castles and apartments. I have some vehicles here, and I have some fruits here. So the question for you, if you can, I see already some answers are happening. Would you put it on A? Would you put it on B? Or would you put it on C? Already somebody got the right answer. Great. Yeah, a lot of people say 5-5 in the fruits cluster, C. Yes, thank you. Thank you very much. You answered correctly. You all get a good grade, because you all figured out that the apple should be in the red, right? Sorry, in the C, in the fruits. And that's why it should be over here. And why is that the case? Well, because you want fruits to be together, right? And in other words, what this is doing is sending each word to a pair of numbers. So it's a word to numbers, and the numbers can be seen as locations. Now, two, a computer can do very well. So a computer can say, well, I can send it to many more, right? I can send it not just to two, but to many. So I've seen embeddings of 4,096 numbers. Okay, you send your word to 4,096 or 1,000 or 600 or something numbers, and you can't visualize that. We can't visualize that, but we can actually like imagine being in 4096 dimensional space and your apple is here flying and your orange is flying close to it and the bicycle is really far away. That's kind of how I picture embeddings. And another way to picture them is thinking that each number describes the word in some way. So if you imagine it like, let's say the first number relates to the color, and the second one to the size, and the third one to the flavor, and the 10th one is something that the computer figured out and we don't. And a lot of them the computer figured out. But if you think of this as a numerical description of your word, then it makes sense that the numbers corresponding to an apple are going to be similar than the numbers corresponding to a pear, right? Because similar descriptions, so they live closely in the space. So that's an embedding. However, embeddings run into some problems. Quiz number 2. So now this is a rapid fire quiz, okay? And you're going to tell me if it's top right or bottom left. So just say in the chat, top right or bottom left, and I'm going to send them fast. So I have a strawberry and an orange in the top right, and on the bottom left, I have a cell phone and the logo of Microsoft. And now I'm going to say, where would a cherry go? Top right or bottom left? Good. Top right. Okay, great. Everybody answer right. Next question. Where would a Android go? Bottom left. Good job. Bottom left. BL. BL is good. I like the acronym. So it goes here. Okay, next. Where does the laptop go? Bottom left, bottom left, bottom left. Right. All right. Everyone's doing very well. Where would a banana go? We're going to finish the door. Top right, TR, TR, TR. Good. Good. Everybody's doing well. Next question. Where does Apple go? Top right? Both? Depends on what we're talking about. Middle? Both? Right? We don't know, right? Exactly. As Apple products or fruit? I just said Apple. I really just said Apple. So we don't know. And this is hard for the computer because it's hard for a human, right? If I stand in front of you in the street and greet you and I go, Apple, you won't know what I'm talking about, right? Because the best embedding in the world will not know if I'm talking about the fruit or the company. The fruit would be on top, the company would be on the bottom. But unless I give it context, a human or the world's best supercomputer will not know if I'm talking about the fruit or the company, right? So the best an embedding can do is put it somewhere. And so we have a huge problem, right? But don't worry, this is a problem that the WhatsApp neural network would have, right? And there's a solution. And the solution is attention. So the attention mechanism solves this problem because it adds context to the words. It modifies the embedding to give it context, because an embedding alone will never do well because there's just no way. I mean, words can be used in many places. So here is in the paper of attention that all you need is attention paper. These are the scale dot product and multi-head attention, blah, blah, formula. We'll get into the details of this, but the way I like to see it is that it uses context. So here is a sentence, and you're going to help me out with this, okay? If I say, please buy an apple and an orange, what am I talking about? The fruit or the company? The fruit, right? Everybody knows the fruit. And if I say Apple unveiled a new phone, then what am I talking about? The fruit or the company? The company, right? The phone. And now help me out. What is the magic word on each sentence that gave it away? Which word was the one that gave you the idea that I'm talking about a fruit on the left, and exactly orange and phone, right? So orange is the word that gave it away, and phone is the one that gave it away. If I didn't have those words, I would still be confused, right? Like if I say, please buy an apple, you still don't know, right? But when I say orange, you know I'm talking about a fruit. So all the words kind of help, but there's a keyword, right? There's a few keywords that really help, and we're gonna identify those keywords. And that's what attention does. It identifies the keywords and then it uses them to pull the word, right? Yes, it's kind of it tells you what category you're in. And this is geometric, right? Words pulls words geometrically. So here it is. The orange, let's say it's here, and the phone, let's say it's here, and our ambiguous flying unidentified apple is in the middle. So when I am on the top phrase, I use the word orange to pull the word apple. And what happens geometrically is that I'm literally taking the word orange and pulling the word apple. Okay, so now I'm not working with the coordinates of apple in this point over here. I'm working with the coordinates of apple in this point over here, because remember, computers don't care if it's apple or anything. It cares about the numbers you give it. These two coordinates, so 8 to 9 or something like that. Like, it cares about the coordinates. On the other hand, if I'm working with the second sentence, phone is the one that gives it away, and therefore I'm pulling the apple towards the phone. So now I'm working with these coordinates. So I've added some numbers here that will sort of give us an idea of, sorry about this. But basically I'm working with different coordinates. I pull the words, and if I pull them, I'm pulling them a very small amount. But if I do this many times, because computers do this, a neural network does many steps of training, eventually it'll get pulled towards where I want it to be. Okay. If there's any questions, by the way, just throw them in the chat and I'll answer them. However, here's a small problem. As humans, we identify that orange is the keyword, but a computer doesn't know. A computer, the word please, the word by, the word and are worth the same. How does it know that it's orange, right? By the way, also just put out a message saying that there's a form for the questions as well. So feel free to send the questions there, and then Modens here can read them to me at the end. So how does the computer know that I should focus on the word orange and not on the word please? It doesn't. It doesn't. It has to look at them all. So it has to pretend that all of them are important, and it has to sort of pull apple in all these directions. Now, why is it that orange still wins? Well, because in an embedding, apple and orange are much closer than apple and please, right? Because embeddings, as you saw before, the apple's close to the orange, right? And so if you, I like to see it like gravity, right? Or like magnetism, right? Two magnets that are close pull each other more than two magnets that are far apart, or like two planets that are close pull each other more than two planets that are far apart. And the same thing happens with embeddings, right? The word apple gets pulled by orange strongly, and it also gets kind of pulled by please, by, and, but not so much because they're far. And so therefore it just moves closer to orange, and orange moves close to apple because this is gravitation in all directions, right? Like this is, I just let the words gravitate. And that's attention. It's letting the words gravitate, just like planets, right? Like obviously the Earth is pulled by the moon strongly and a little bit by all the other planets, but they're so far away that they don't pull it that much. So therefore the Earth and moon pull more, and the others kind of stay there. They move maybe 1 tiny centimeter, and that's it. But it's not comparable to how much the Earth and the moon pull. So for example, if I've talked about fruits for a long time, somebody mentioned the context and categories here. If I've talked about fruits if I've been talking about fruits for an hour, I'm obsessed with fruits and all I talk is about fruits, and then I say apple, well, I'm very likely talking about a fruit. Maybe not, but very likely. And that's because I have a galaxy of fruits here that will pull my apple all the way, and now I know where I am, right? And apple also pulls them, but we have a strong galaxy, So in attention, you let words gravitate by themselves as you train the neural network, right? So you train the neural network, you let words gravitate, you train the neural network, you let words gravitate, and that's how you're adding to the computer a sense of what you're talking about. Okay. So that's pretty much attention. There's a context. There's an example that people always use in attention, and I try to look at it geometrically. You maybe need a little bit of faith here for this example, but I like this example because it says the bear ate the honey because it was blank, and the question is, what is it? what is it referring to, right? Like, so what word do you think it is talking about? The berry, the honey, because it was, could be honey, right? The honey was, but it could also be the bear, right? We don't know. We don't know if we're talking about the honey or the bear because there's not enough context, right? So it could be the bear, or it could be the honey. So we need one more word. So if I say the bear ate the honey because it was hungry, well, now we know we're talking about the bear because the bear was hungry. What if I say delicious? The bear ate the honey because it was delicious. Now we're talking about the honey, right? So therefore, and I love that everybody's answering the questions real quickly. So therefore, I need the context, right? And so I like to see this in geometry. What is really happening here in terms of the attention? So I imagine that the words are flying around, and it could refer to honey and bear. And there is distances to all of these ones, but if we just want to kind of forget them, let's say they're far away, just for the sake of this example, it gets pulled by honey and by bear, but it doesn't really know where it gets pulled more because it's, let's say it's equidistant. I need your help with imagination here, but bear with me. If I say the bear ate the honey because it was hungry, well, in an embedding, think about this. Hungry describes a bear, and so hungry and bear appear more often than, let's say, hungry and honey. Let's say hungry is closer to bear. So now I get pulled twice as strongly to this direction. So therefore, it gets pulled many times, and it gets closer to bear. So we figure out that it is relating to bear. On the other hand, if I say delicious, well, delicious appears with honey more often in sentences in the same context, so it's closer to honey. And now I get pulled twice as much in this direction than in this one, and so then it becomes descriptive of honey in the embedding. Of course, I needed your help with imagination here, but you start seeing how gravitation really adds context to things. So if you're looking at context when you're talking, and gravitation of words flying in space, and how this is gravitation is how you put them into the neural network, then that's the right thing. There's a lot of details, a lot of mathematical details, but anyway, again, feel free to stop me if any questions. I'm going to get to something called similarity, because I've been mentioning a lot about distance, right? I've been saying words are far apart, words are close, words are, but in reality, that's a good way to see it. But in reality, neural networks and embeddings don't do distance because it gets confusing. They do something called similarity. And there are many ways to measure similarity. So I'm going to give you 3 ways to measure similarity. But basically, you can think of it as kind of the opposite of distance, right? If cherry and orange are close by and phone is far away, then there's a high similarity between cherry and orange and a low similarity between cherry and phone. So high distance, low similarity, low distance, high similarity, right? And then I see some questions. I'll pause every now and then and answer them. So here is a little example of an embedding, and I'm going to show you 3 ways of measuring similarity that are actually very similar. Let's say we have an embedding, and we have the descriptions of the embedding are the horizontal axis measures how much tech there is in the word, and the vertical axis measures how much fruitness there is in the world. It's a very simple embedding. And so, for example, an orange and cherry are in the fruitness side, and the phone is in the tech side, right? And I want to calculate the similarity between these 2 words. So I'm going to do the following, okay? If you've seen dot product, this is dot product, but this is how I see dot product. Let's say I want to calculate how similar cherry and orange are, and cherry is in the coordinates 1, 4, and orange is the coordinates 0, 3. And so what I do is I remember that the first coordinate is tech and the second coordinate is fruitness, and so I multiply the tech values 1 times 0, and I get 0, and I multiply the fruitness values 4 times 3, and I get 12, and then I add them, so I get 12. So because these are similar, the high numbers are in the same places, and so I get a high number. But let's see what happens when I do cherry and phone. Well, cherry has high fruitness and phone has high tech. They don't match, right? So if I do 1 times 3 and 4 times 0, then I get 3, which is a much smaller number because the high points don't match positions. And it's even worse if I do orange and phone, because orange is 0, 3, and phone is 3, 0. So therefore, I have 0 times 3 and 3 times 0. Yeah, I see people commenting on the numbers. Correct. 12, yes, bigger than 3. So I have the big dot products for words that are very similar because the numbers match in high positions. And when they don't match, I have words that are not similar. They have bad small dot product. So dot product is a measure of how similar two words are, right? There's another one, which is cosine similarity. I'm aware you may have seen all of these, but just throwing them out there again. What is the cosine similarity? Well, it really says don't worry about the distance, worry about the angle from the origin. So the angle here is 14. It's a small angle because they're close. It's a small angle. And I do cosine. Cosine is big for small numbers and small for big numbers. So it works. And so therefore the cosine is big. It's 0.97. Whereas the similarity between cherry and phone is 76 degrees here. So it's cosine of 76, which is 0.24, which is much smaller. And when things are perpendicular, that's when they're 0, right? So the cosine of 90 here is 0. So you can have negative similarities, right? It could be all the way to -1. So anything from 1 to -1, where 1 is the same word, and all the way to -1, which is very different. And so this is another way to measure similarity. They are actually the same way. Dot product and cosine similarity are the same way if I do one tiny thing. If I normalize everything, so if I bring every vector down to the unit circle, and I just scale everything to have length 1, then dot product and cosine similarity are the exact same thing. You can do some linear algebra and realize that they're the exact same thing. So I could normalize all my vectors and do dot product, or I could do cosine similarity. Those work better than distance because sometimes you have vectors that are very similar and one is longer. Like, for example, if I say apple and then apple, like a long one, it could be the same vector, but much longer. Or like a long paragraph may have a long vector, but it could be relating to a small paragraph. So sometimes distance is not the best measure, but cosine similarities is much better. So that's why we use it. And actually, this is the math mul here, the math multiplication, because it's a dot product is a product of vectors, right? Believe it or not, and I don't exactly know why this is the case. I have a guess. The one they use in the paper, in the attention is all you need paper, is neither dot product nor the cosine similarity, or somewhere in between. Oh my god, I got that zoom. This happens every time. Every time I count
Session
with
is
my
going
fingers.
amazing. So the
Yeah.
Meg is saying it the wonderful.
It was the dot product is so amazing that the Zoom got excited and did fireworks. So I have the dot product, which gives me 12. What they do in the paper is they do something in between. Okay, they do something in between, which is they divide not by the length of the vector but by the number of entries square root. So for example, here I have two entries that are 1 and 4. I divide by the square root of 2. So here I divide 3 by the square root of 2 and 0 by the square root of 2. And that's the dot product that is used. So for example, if I have an embedding of length 1,000, I divide everything by the square root of 1,000. So it's in between. Cosine similarities is small because I'm dividing by a big thing. Actually, I'm not sure. Strike that. It's something that divides. It's dividing by the square root. And I think the reason for this is probably because they tried a bunch of things and that's what worked, which is the answer to so many things in machine learning. But it's just to make it small, right? Because if you have a vector that's too big, your results are too big, but then you want to divide it so that numbers are manageable. That's probably what it was. But if you ever when you see, I'll show you when the square root thing appears. Now, let me tell you more about that gravity calculation that we did. The gravity calculation, I kind of called it gravity, where the formula is m1 m2 times some gravitational constant divided by r squared. Obviously, that's not the case here. In here, the case is a different formula that has similarity built in. And the formula is this. If I have apple, it becomes apple, but I add a little bit of orange, which is orange times the similarity. And that's why when I have big similarity, I'm changing the word a lot, And when I have small similarity, I'm not changing the word a lot. Let me get to this. Okay, so, and I always normalize it so that I have a percentage. So apple becomes a percentage of apple times the remaining percentage of orange. Let me elaborate. Let's say if I have far apart words like apple, if I have words that are similar like apple and orange, then orange changes apple a lot. But if I have apple and truck, it doesn't change very much. And the reason is that it's not similar. So let me do a small calculation with some imaginary, well, real numbers, but that I imagined. Apple and orange are similar, and apple and truck are not similar. So let's just say, I'm going to do this formula. Let's just say that the similarity between apple and orange, I've calculated it, and it's 0.7 because it's big. And the one for apple and truck, it's negative. It's negative 0.1 because they're so different. It's negative. Okay. So I'm going to change apple to apple, and I'm going to add 0.7 times orange. So the similarity times orange. And for truck, I'm going to do apple equals apple plus minus 0.1 times truck. Okay. Now, I don't want to subtract stuff, so I want to make this positive. This is a trick that we use a lot when we want to take negatives into positives. And actually, it's a good segue because Wamik asked me if we can convert distance into probabilities. This is how we convert distance into probabilities. We use the Softmax function. How many people here have seen Softmax? Give me a yes in the chat just to have an idea. If you've seen Softmax, what happens with Softmax is that it takes numbers and raises e to the number to make everything positive. So instead of 1, I'm going to have e to the 1. And instead of 0.7, I'm going to have e to the 0.7. And here, instead of 1, I'm going to have e to the 1. And instead of negative 0.1, I'm going to have e to the negative 0.1. And now I'm going to normalize because I remember I wanted everything to add to 1. So I divide by e to the 1 plus e to the 0.7. And here I divide by e to the 1 plus e to the 0.1. And so on the left, I have apple becomes 57% apple plus 43% orange. So it changed a lot. It moved towards orange linearly, the line that moves it. And apple didn't become that much truck because it got 0.25%. Obviously, the numbers would be much smaller in reality, but you get the point, right? The more similar, the more it pulls. So this is the equivalent of gravity. It's not m1 and 2 divided by r squared, but it's, add the similarity times the other word, e to the that, divide by the thing to normalize, and you get that. So that's what I meant, right? Like when I said apple becomes 57% apple plus 43% orange, it means that I move the word apple 43% along the way towards orange, okay? Because I'm talking about coordinates. And when I say apple becomes phone, let's say it becomes 64% phone plus 36%, sorry, apple plus 36% phone, then I'm moving it 36% along the way, okay? Are we clear? Let me, since I'm changing topics, I'm going to answer questions that I see here. Ian says, please get Apple along with Samsung. How would the model differentiate? Yeah, we can always trick the models, right? Like, I find that we can always find a sentence that will trick the model. You could be telling somebody to buy an Apple in the store and a Samsung phone, or you could be, you know what I mean? Like, this is not 100% work all the time. But imagine that you're writing a long essay, then I think it's harder to get confused. But it still gets confused. ChatGPT still gets confused when we tell it things. And then Wamik says, can we convert distances into probabilities? And the answer is yes. The softmax is what does that, right? It converts it into probabilities. All right. Any other questions? Mo, is there any questions in the chat? I said it may be a good time to sort of make a little pause, or how's everybody doing?
Yeah, hi, Luis. We have some questions. Let me read out for you.
Sure.
In the context of AI rapid development, how do you envision the future interplay between LLM and human cognitive process, particularly
Ooh.
in creative and problem-solving tasks?
Oh yeah, we're opening a door there. Yeah, I think
Yeah.
we can probably leave that for the discussion. I would love to talk more about that in the discussion at the end. But yeah, I mean, I feel like ChatGPT is definitely doing a lot of our cognitive stuff. It's doing a lot of our cognitive stuff, and I think that's an opportunity for us to sort of see what, use it as a tool. Maybe some skills may not be useful for the next generation. Maybe math, maybe writing, or not so much. So I feel like
Yep.
I can get philosophical, but I do feel like things like soft skills, things like empathy and things like intuition, things like other things are gonna rise, because this is what ChatGPT cannot do. ChatGPT can take decisions based on data better than us.
Yep.
So science, it'll be easier for it. Math will be easier. But let's table that for the discussion, because we can really go down the rabbit hole. But yeah, it's a great question.
Yeah.
Yeah. By the way, how are we doing with time? What about half an hour? Are we sort of?
Let me ask, Sujit, how much time we have?
It's around 50 minutes.
We have
50?
50 or 15?
50, 50.
Oh, that's great.
Oh, perfect. I can ramble for a long time. Okay, excellent. So let me get into some problems, because we're still having some problems. We have the embedding, which works really well. We added attention, which works really well, but there's a problem. Sometimes embeddings are just not that great. We are doing very well with embeddings, but we can improve them a lot. There's a lot that can be improved. And as a matter of fact, what we're going to do is, let me ask you a very loaded question. Do you think one embedding is good enough for what we do? Should we use one embedding? No, I see Mo is like shaking his head. It's like, absolutely no. Everybody's like, no. Why should we use one embedding if we have lots of computers and lots of computing power? So let's try to use more embeddings. Okay, what do I mean by an embedding could be good or bad? So let me give you 3 embeddings. I have a quiz. I have the first embedding, and my goal is still to figure out what's the apple, if it's a company or a fruit. I have embedding 1, candidate number 1, candidate number 2, and candidate number 3. Now you can tell me which one, 2, or 3 is the best embedding for our problem. Perfect. Everybody here is a genius. Yes. Number 1 is the best, right? And why is number 1 the best? Because it's the one that separates the worst best, right? Which one is the worst one between 1, 2, and 3? Which one's the bad one? The one that you don't want to work with. 3 is pretty bad. People say 2 seems like there'd be a consensus on 2. They're both pretty bad, but yeah, I agree with you that 2 is even worse, right? So 2 is the worst one, and 1 is like so, right? Why? Well, because if I want to separate apple and apple, embedding 1 does it beautifully, right? If I want to separate apple and apple, embedding 2 doesn't do it very well. It keeps them very similar because it's not good, right? It doesn't separate them. And then embedding 3 is so, right? I'm sorry. Embedding 3 is so because it kind of separates them, right? So we want a bunch of embeddings, right? We want a bunch of embeddings. How do we use a bunch of embeddings? Well, I could go around asking people for embeddings, right? Like maybe the group at Codecrafters have built a great embedding. So I go, hey, Mo, can I borrow your embedding? Then I go to Google and I say, hey, can I borrow your embedding? And I go to Cohere and I go, hey, can I borrow? And I can just get 10 embeddings and make them vote or average out their results, right? I'd be like, I could, but that's not the right thing to do, because embeddings could be different. Maybe the Codecrafters embedding is of length 2000, and then the one at Google is of length 1000, and I can't compare them. It's hard to. One is, I don't know what, I want to work with a lot of embeddings, but I want to work with embeddings that I can handle. And let's just say that I only have one. I only have one embedding. So what can I do? I can build embeddings by modifying existing embeddings. Okay, so I'm going to take an embedding, my embedding that I have, and it's all I got. And from that one, I'm going to build a bunch. How many? In the paper, they did it with 12. I'm going to do 3. Okay. And how do I do it? Well, with linear transformations. Okay. Do you know what linear transformations are? If you've taken a linear algebra class, linear transformations, they're matrices. A matrix is a linear transformation, but I like to see them as image, like moving images around. So if I have this image of a dog, I could rotate it. That's a linear transformation. That's a 2x2 matrix that rotates at any angle. I could stretch it in the horizontal way or in the vertical way or pretty much in any way. A 2x2 matrix tells me how to do that. And there's another type of transformation, which is shear. Just imagine you have a book and you fix the bottom and then push the top, right? Right? So it does this, it shears. That's also a matrix. And every matrix is a transformation, and every transformation is a matrix, okay? And if I combine them, if I do rotating, stretching, shear, then rotate again, then shear again, then I get pretty much anything I want, right? Another way to look at it is you have two fundamental vectors here, the blue one and the orange one. So if you send the blue to any vector and the orange to any other vector, and then this square becomes a parallelogram, and then the tiling of this with the square becomes a parallelogram tiling, that's how you switch the plane to the plane. And you couldn't make it into a line if you generate. That's fine. That's just a singular matrix. And you can think of that in high dimensions, right? If I have a space of a 3-dimensional space, I could also rotate, stretch, shear. And if I have a 4096 dimensional space, I can think of a 4096 by 4096 matrix that linearly transform my space into something completely different. At the end, it amount to a bunch of rotations and stretchings and shearings and high-dimensional things, right? But that's how I do it. So I can get new embeddings from existing ones. So let's get, from my original embedding, let's say my original embedding is this. It's not so good. And I get this one over here, and I get this one over here. So quiz, out of these three, which one is the best? Yes.
Third one, yeah.
You all got it right. People get it right. Yes, you all got it right. The best one is number 3. And just to keep us going, which one's the worst? Two is the worst, right? I agree. Yeah, it's harder to see, but 2 is the bad one, right? And just like before, right? Like the first one, the one we have is okay. We made it worse by doing the first transformation, but we made it better by doing the third transformation. And so what we're gonna do is we're gonna do a bunch of embeddings. Some of them will improve, some of them will not improve. And then we're gonna have a way to train the embeddings as we train the neural network and start noticing which ones are the good ones for which cases, because maybe for fruits, the third one is better, but for like cars, the first one is better, and be able to make them sort of vote. So we're gonna have a way to say, this for this particular case, use the third one 80%, and the first one 5%, and the second one 15%. But for this other case, the first one 95%, So, and this is all stuff we train in the big neural network, right? And to make this easy, it's the key and query and values matrices. That's what they do. They modify the embedding. And so if you see this on the left is attention with only one embedding. So the matmul is the dot product, and then the scale was that the softmax is the one I showed you, the softmax, etc., etc. And this is multi-head attention, where you have matrices KQV and in a bunch of different embeddings here. So let me get into this. And by the way, yeah, when you see the formulas, you see the square root of dk, right? This is the square root of the length of the number of entries in the vector that I told you. Everything can be seen here, except that the formulas, they just hide it, But if you look at it, it's all geometric. But anyway, let me tell you about key, query, and value matrices. These are a bunch of matrices, keys, queries, and values that store these transformations. So let's look at keys and queries. Keys and queries work in the following way. Basically, I have my 3 matrices here, the okay one, the bad one, and the good one. And what I'm gonna do is, excuse me. What I'm gonna do is I'm gonna modify the similarities. Okay, so when I do similarity, let's do dot product, right? Here's my vector for orange, and here's my vector for phone. And the similarity, remember I calculated this as a dot product, right? Like if you're used to linear algebra, dot product is this. And if you scale it, I'm gonna be a little hand wavy here. It's kind of like an angle, right? If I scale it, is the cosine of an angle. In this linear transformation over here. Now, what I want to do is I want to multiply the first word by the matrix of keys and the second word by the matrix of queries. And now my similarity is not it's still the first vector times the transpose of the second one. but the transpose of the second one now has a matrix there. And if I just look at this product of two matrices, that's a linear transformation that sends this to this. And now I'm calculating the similarity in a different space. Okay, so there's a little bit, I'm putting a lot of linear algebra here. This is something that can be sort of like, we can talk more about it if you'd like, but basically think about the matrices key and query are building us a linear transformation. And therefore, we are not calculating the similarity in the original, we're calculating the similarity in a modified embed. Okay, and and now we have them over here. Oh, sorry, I think I may have some slides happening twice. Apologies. And those are the key and query matrices. Some people like to see them differently. I think when I ask experts, they tend to see the key and query matrices as a sort of like a database. Like you query a database with the key, and then you get a result, and then the value is what comes out. That's a good way of seeing it. I like to see everything geometrically, so I try to translate everything to words moving around. But if you see, like if you read the paper, they normally talk about more in the database language. And the value matrix is one that it was I have to admit it's hard for me to understand it, and I talked to a lot of experts and I asked them a lot of questions, and I think I have a sort of idea of what the value matrix is, but it's not as concrete as what I have for the other one, so bear with me. The value matrix, what happens is the following. When you're working on your embedding is optimized for similarity of words. Okay, so it knows when words are similar. But when you want to talk, it turns out that using one of those embeddings is not the best. What I've heard the experts saying is that when you want the model to talk, you want to use an embedding that is optimized for what's the next word. And so that's what the values matrix does. So we're going to use similarities in an embedding that's optimized for similarities, and talking in an embedding that's optimized for talking. Okay? And so that's what the values matrix does. So this embedding on the left is optimized for similarities. This one is optimized for finding the next word. And the keys and queries help us with the similarities. The values help us with the next word. And what happens is that we have a matrix V that turns our embedding that's optimized for similarity into an embedding that is optimized for talking, for finding the next word. And so I know that's up in the air, but that's as much as I understand. So let's and so at the end, what happens is this: you have the key and query matrices, right? And you use these to find the similarities using the dot product. This KQT is a dot product, right? It's a matrix product. And this square root of dk is the normalization that I told you. And then you find the similarities here. Then you go to this stage, which is when you move the words around using Softmax, okay? And then you use the values matrix to turn this embedding into an embedding where you're gonna use to find the next word. So that is scale dot product attention. Now, what's multi-head attention? Well, I have a bunch of KQ matrices. In the paper, they have 12. Here we have 3. Each one gives us different similarities. Then we use the values to turn that into embeddings that are optimized for finding the next word. We move the words there, and then we concatenate. So what's concatenate? Imagine this. Imagine that each of these matrices in this game, it's 2 by 2, right? Each of these spaces is 2-dimensional here. So I have a bunch of tables of 2 columns. If I concatenate them, I have a table of 6 columns, which gives me a 6-dimensional space, right? So I have a 6-dimensional space. That's too big because I can't just concatenate things and get something humongous, right? So I take a linear map, I multiply that by a 6 by 2 matrix, and I bring it down to 2 again. And I bring it down to my original size again. So if I have a bunch of 100 by 100 matrices, I concatenate them, and then I bring it down again to 100. And this part learns what is good and what is bad. So it says, you want this much of the first one, this much of the second one, this much of the third one, etc. So for example, the the good embedding becomes multiplied by a lot, the bad one by a little bit, and the middle one by so. And that's how you sort of put them together. And so that's multi-head attention. A very hand-wavy way, but feel free to throw any questions in the chat if everything's not clear, but that's sort of kind of how I see it geometrically. And now, as I mentioned before, how do you get these matrices? They get trained the way a neural network gets trained. Okay, so they get trained in the process, right? Like in every step of training the neural network, between every two layers of the neural network, you have an attention layer. And you're training the K, Q, and B in the same way as you train the neural networks using backpropagation. So it's a mess, but it's how it's done. Okay, and here is the attention, and the feed forward is the blue one, or as I like to see it in my little diagram, attention is at every layer of the neural network. That's all I'm going to say about attention. Feel free to throw in any questions. That's the hardest part of the talk. Feel free to throw any questions. Yes, go ahead.
Yes. I have some questions. So when we
Yes,
are
please.
talking about the kind of the attentions, and we are doing a transformation or linear transformations, so how we are comparing it? Okay, this transformation is good or this transformation is good, and then we can take this part. So it's kind come up on the fine tuning, or how we gonna do this part?
Yeah, that's a great question. I mean, that's kind of a similar question of like what happens inside the neural network, right? Like, why does this node know more than this one about apples, yet this one knows more about other things? So it's my answer. Unfortunately, it's as much as I can answer the other one, right?
Okay.
When you train a neural network, you trust that it'll find some good transformations that work for some things and some good for others. And that when you're in a certain word, like in a certain topic, then it'll sort of highlight the ones that are good for that and low light the ones that are not. And so it's a bit of the same faith we used to trust neural networks. We used to trust neural networks with attention. I'm sorry, that's as much as I got.
Makes sense, yeah.
Okay, cool. All right. Any other questions? Anything else? You can always throw them in the chat and I'll answer them in real time. So I think for the rest of the time, I have two more things, and I believe I have about half an hour, right? So I'm gonna tell you a little bit about these other three steps: tokenization, embedding, and positional encoding. And then I'll tell you a little bit about fine-tuning the LLMs and how to use them for, you know, removing hallucination and stuff like that. I'm kind of breeze through these three because they're more clerical, really. Tokenization is an important step, but in reality, like what happens is that you don't work with words, you work with tokens. So each word is a token, except that some words become more than one token. It's a word to simplify it. So for example, the word doesn't becomes the token does and the token int. There is a science on how to make the best tokenizations, but I think it's worth studying, but I think I'm gonna sort of pass through it today. But basically think of it as everything turns into the thing turns words into tokens, and then the tokens are the ones that go into the embedding. There's something positional encoding as well, which is I find it a little sloppy, but it works, to be fully honest with you. Omi says what means to be one token only. It's just pretty much a word becomes it's kind of like a pre-recorded thing with that the model uses. I don't know. I think it just works better when you turn things into token. But if I take a word, it becomes a token, but some complicated words become more than one token. That's pretty much others. Positional encoding, what it does is obviously if I have a sentence and I rearrange the words, I could change the topic completely. And so what I do is I modify each word in a different way. So for example, write a story period is not going to be the same as story period a write or something. So how do I tell them apart, right? This, as I said, it's kind of sloppy, but it's something that you have to sort of believe that the neural network learns. So I take my embedding, and embedding wise, they're the same thing. So the embedding forgets the order. So what do I do to remember the order? I'm going to say, take the first word and modify it in way one. take the second word and modify it in way 2, the third word modify it, and so on. So for example, I can say the first word, move it in this direction, the second word in this one, and so on. And now it changes the embedding, right? Because I'm doing something different to every word. And the idea is that if we do it in a way that's sensible, the computer starts learning this sequence that we do. So if I do it in a way, for example, this is a sequence, right? Like I'm kind of rotating them, and you can use signs, you can use e to the something. If I use a sequence, the model starts kind of learning the sequence and being able to tell what was the first word, what was the second word, what was the third word. Pretty much that's it. So there's a science to positional encoding, but I'm also gonna breeze through it. And then the softmax, we pretty much talked about it already, but it's to answer the question that I saw before, is how you turn these scores into probabilities, right? Because if I say in the store I bought an apple, the computer can say apple, but I want it to sometimes say orange or elephant, anything, like a lot of different words. And what I want is that the computer gives a score. So for example, high for apple, low for elephant, because I'm not going to buy one in the store. And what it does is it turns scores into probabilities, because I want it to actually give me probabilities for all the words, because I wanted to answer different things every time, but I wanted to give me the words that are high score, high probability. So what I do, the trick, take everything and multiply it by, divided by 4 plus 3 plus 1 to get my probabilities. And I could get this, but again, I could have negative scores. So how do I turn things negative into positive? The trick I always do, e to the that, okay? So I can't do this because I would, sorry, I'm getting ahead of myself. If I have a negative score, I could potentially ruin the denominator, right? Because I don't want to divide by 0. So I just take everything and take e to the score, okay? So e to the score, I have e to the 4, e to the 3, e to the negative 1, and then I divide by the sum. And so I get a bunch of probabilities. So in summary, if I have a bunch of scores for words, I raise e to the score to make everything positive, and then I divide by the sum of e to the all of them, and I get a bunch of things that add to 1. So the big neural network, that when I tell it how are, it responds u in reality is having a lot of scores, doing e to the score, then dividing by the sum, and getting a bunch of probabilities. And the words with high probability are likely to be the next word. It could sometimes throw a word with small probability, but most likely it'll be adding words that are high probability. So that is the end of the, basically that's the end of the architecture of the transformer. Next, I'm going to talk about fine-tuning. But if you have any question, I think I'm going to stop here and answer some questions about the architecture of the transformer. I think I had some questions here. Swati says, why is orange multiplied with keys, not queries? So it's just random. It's kind of random. I think you multiply one by the keys and one by the queries. I think what matters is that you multiply one by one matrix and the other one by the other matrix, so you have room to learn. But that's about it. When we asked about questions about tokens, which we answered. Sandeep says, is this the first time the potential of the attention mechanism was realized? What was reception of the attention mechanism before this transformer paper came out? That is a great question, Sandeep. I think attention came out of that paper. It could have been that it was alive before. It was never, a lot of things in machine learning sometimes exist mathematically, but only until they have big enough computers and big enough data sets, it started working. Like neural networks existed for a long time until they started working one day. So I don't exactly know if attention existed or it was defined by this paper, but the fact is that this is really what did it. Like attention is really what kickstarted this new behavior of LLMs. But that's a good question. I'll find out. And then Sandeep also says, which part of the original transformer architecture has been tweaked since, and which parts are kept the same? Oh, that's a good question. I think all of them are tweaked. I mean, there's people who work on making better tokenizers. There's people who are constantly working on making better embeddings. That's the goal. I would say embeddings is the most powerful work you can do in these things because it helps every application. Everything is tweaked, you know. I think and also there's new things, right? Like people are working on things like the name escapes me, but SSMs. Do you remember the acronym? Is it the state space machines, I think? So everything is getting tweaked right now. I wouldn't say anything's starting to be kept the same, but I think two things happen. You make the steps better, and you try to come up with a new, different architecture. Yeah. All right. Any questions that came out of that about transformers, Mo, that you think we could answer, or should we be more for the end? We're good. All right, so let me get to the last part of this, which is the fine tuning. So it says basically you have trained your neural network, you made it read the entire internet, and now you see how it's gonna do. And the answer is terribly. It's still doing terribly. And one reason is that the internet is not a question and answer repository. So I'm gonna ask you a question to an LLM that we've trained using the internet, and say, what is the capital of India? And you know, we all know it's New Delhi. But if you have a model that is answering one word at a time, what are possible words that could be the next one after this question? What is the capital of India? What words do you think could come after? Like it could be the word new, it could be the word Delhi, it could be the word the, because you want to say the capital of India. The is a good one. It could be because let me tell you what the cap. But if you've read the entire internet, what about the word what? The word what? Yeah, next question. George is getting there, right? There's a lot of quizzes in the internet, and it could be a quiz that said, what's the capital of India? And the next question is, what's the capital of somewhere else? So the computer says, I read the internet, and I think the next word you want here is what, because you may be in the middle of a quiz. But no, we're asking a question, right? So like the next word could be a lot of things. And the computer learned, the model learned to say the next word. It didn't learn to answer questions. It doesn't know it's answering a question. It just knows what the next word could be. So this can be pretty chaotic. And the answer is, don't worry about the architecture. We've done all the smart stuff we can in the architecture. Now worry about the data. So this is the expensive part. Hire a bunch of people, get them to write a lot of data sets where there's questions and answers. Okay, so give it question and answer repositories. Okay, and train your model using those. And when you give it a lot of those, the model starts picking up that when it has a question, it should answer with the answer instead of making fun of you by saying, oh, I think you're in the middle of a quiz. Let me say let me ask a different question, right? So that's it. Now we're more like data. And this is the hard stuff, you know? This is like when you see companies that work on LLMs, a lot of their work is putting the right data so the LLM does the right thing. For example, if you make a chat, you say, hello, how are you? And it says, good, and you? And then it stops talking because it doesn't know that you're supposed to remember stuff from the past. It doesn't know that it's supposed to, you know, it has the power to do it, but it doesn't. So what you do, you give it a lot of data sets of long conversations, okay? Same thing for commands. You know, if you say, translate this, it doesn't know you have to translate this. You know, if you say, rewrite this, help me with blah, blah, it doesn't know you're giving it an order. It may just give you another order, right? So you have to give it a lot of data sets where there's a command and the order given, and the command being executed. So a lot of that, and that's a very interesting part, and that's where a lot of the money goes for, like a company training LLMs. Excuse me. But there's still problems. Even after you do this, even after you fine-tune it and fine-tune everything, there's still problems. And what's the main problem that you've seen in, like, let's say ChatGPT? What's the main complaint, where the memes come out, where the funny part? What's the main thing that LLMs do? Let's see. George got it right. The hallucinations. They hallucinate, right? They go in crazy directions. and people think that they most of the time are correct, but sometimes accidentally hallucinate. And I think it's the opposite. I think they always hallucinate. And sometimes they accidentally hallucinate the truth, right? Because they're not meant to be databases. They don't store information. They know what the next word is likely to be. That's it. They're not a database. They're not to be trusted. Sometimes they see data so much that they correlate it to the right answer. And that's what we see. But in reality, there's nowhere that stores the right answer. So if you ask it for a date, if it appears many times, yes. But if I ask it for like something popular, like I don't know, an illness that appears a lot, it will give me the right treatment and stuff like that. But if it's one that only appears in one research paper, it has no reason to learn it. But it knows how to talk confidently in that topic. And it doesn't know if it's right or wrong. So we got to watch out. And we got to do a lot of things. And I'm going to teach you some things you can do to reduce hallucinations. So I like to imagine the transformer as a person. So it's a person that read the entire internet. So it knows a lot. Imagine if your friend read the whole internet. It knows a lot of stuff. So it's very good at following instructions. But it's also unreliable with facts because it's not to be trusted. And it compensates that with an excess of confidence, which can be good or bad, right? So I imagine that I have a friend who does that, who knows a lot of stuff, but it's unreliable with facts. But no matter what, they will always answer with full confidence. How do I help this friend? Okay, let's call him, it's ChatGPT. Let's call our friend Chat. And let's say that, can you give me some ideas? So let's say we want our friend to be, we have a company, and we want our friend to be the public relations person. So he'll be the customer support. And the friend is really fast. So they can answer the phone, answer messages, talk to people, and chat very quickly. But they have the problem, which is that they're unreliable with facts, but they're very good at following instructions. How could we help this friend? Any ideas on how you would be able to help this friend? Want to take ideas on the chat, see if what comes to mind. And we're thinking about a person. Don't worry about this being a computer. Tell me, how would you help a person, right? Yeah, so because it's good management, right? Like we could give them good instructions, right? Like we could give them good training. So one thing we can do is, in front of them, we write a big set of instructions. And the instructions said, you're a respectful chatbot, when you ask this, answer this, check if there are more questions, don't answer in a rude way. That's one thing. So that's called a preamble. We can do a preamble, right? Yeah, governance it says can do that. That's like good. Rainbow says tell others to cross check. That's a key step. Yes, I'll get to that in a second. We can send our friend to more training, right? Because if we have a company that does anything, a particular thing, thermometers, and then we send them in a training where we teach them about thermometers, so this is sending to extra training. That's called fine-tuning. So fine-tuning is simply you take all the data from your company, all the PDFs, all the documents, and then you post-train your LLM with that stuff. You take the LLM from ChatGPT, from Cohere, from OpenAI, or from Anthropic, you post-train it with a bunch of data from your company. And now it's almost like it went to grad school, right? And then another thing you can do, which is the one I'm going to get to, is, well, it's good at following instructions. So you can say, hey, don't answer before. You first go and look up the answer, okay? So you search in the documents, you search in Google, you search on Wikipedia, you search on the page of frequently asked questions of the company, you tell it what to search, and then you find the answer, and then you answer from that answer. That's called RAG, Retrieval Augmented Generation. And Retrieval Augmented Generation, until now, is the best that I've seen against hallucination. And it pretty much, I'm not going to say all the time, but I've seen it like basically remove hallucinations completely, because if you ask it a question, it first searches on Google, on Wikipedia or something, comes back with the answer and answers from there. So it's it's very hard to mess that up. So a preamble basically, let me get through this in detail. A preamble basically says, you give it all this text, and every time you have you ask something, it reads the text of instructions first, and then it replies. Fine tuning basically says, okay, I took my transformer, I completely trained it with the internet, and then I trained it with curated data sets like the question answer, the command, everything. And then I train it with my own data sets. Okay. And then retrieval augmented generation basically says, if you ask it what's the capital of India, before you answer, you search on Google, then you take the results of Google and put them in the prompt and say, what's the capital of India? But answer from this. And then it has no other way than answering the right way. Okay. Do I have about 5 to 10 minutes? I can talk about search, or I can stop right now. How do you feel on modern and
I guess, Sujit, I guess we have a time, right?
Yeah, we can continue. Sir,
Okay,
please continue. No problem.
let me talk about search very briefly, and then we go to questions. Because I mentioned something, right? I mentioned search on Google, search on Wikipedia, and search. It's not that easy either, right? So let me tell you about search. How would we build a search engine? So let's say that my search query is the word Brazil to USA travel visa. Okay, and I retrieve 2 articles. You can tell me which one is better. Article 1 says USA to Brazil travel visa, and Article 2 says visas US Embassy in Brazil. Which one is better, 1 or 2? Let's see in the chat. 1 or 2? So there's some 1s, but there's more 2s. Yeah, I think it's tricky, but I think, and it's tricky, and it shows that search is tricky. But 1 doesn't really do it, even though it looks like, because if I want to travel from Brazil to USA, it's completely different story than from USA to Brazil. If you tell me what the paperwork is from one direction, I don't know anything about the paperwork in the other direction. On the other hand, the second one is more likely to have the right answer, right? But it's very tricky. And what happens is that the first article has the exact same words as the query, but in different order. And the different order changed the meaning completely and made it useless. So this is called keyword search. And it's what's been used for a long time. I mean, I think that's how internet search started back in the day. And many advanced places have keyword search. When you search for products and stuff, and you get something completely wrong, but it matched the words, and it's like, come on, I wasn't looking for this. But in the other hand, semantic search is the second one. It's really called the dense retrieval or semantic search. It's the one that does much better, and it uses an embedding. So let me tell you about embeddings. So I told you about text embeddings for words, right? That they send a word to, excuse me, they send a word to a bunch of numbers. But you can actually do this for longer piece of text. You can do it for sentences, for paragraphs, etc. And it sends the sentence to a bunch of numbers, okay, which I like to imagine as like they're flying around, right? So like sentences are now the ones flying around in space, and sentences that have similar meaning are here, and another similar meaning are here, even though the wording can be completely different. And so if I put these 3 things in an embedding, well, the embedding would know that the sentence Brazil to USA travel visa and USA to Brazil travel visa may have the same words, but the meaning is completely different because embeddings find meaning. And so therefore, on the other hand, these 2 are close because they mean something similar. So embeddings are very powerful. And searching in embeddings is really just nearest neighbors, right? I have a bunch of documents flying around in space, and I have a question, and I look at what's the closest, okay? And I respond with the closest ones. So for example, this is something I did in the Cohere one. I have 4 responses. The capital of India is New Delhi, apples are red, Galileo invented the telescope, and a square has 4 sides, and I put them in an embedding. You can play with this in the Cohere playground. And I said, what's the capital of India? And it put it here. So the closest sentence is this. And so that's semantic search. And it works really, really well. Of course, everything I say comes with a problem. There could be problems here. Everything I say, don't ever think of anything I say as the final thing. There's always a problem, but we solve it, right? What could be a problem with dense retrieval? Can somebody help me of what could be a problem that you can have the best embedding, the best dense retrieval, and it messes up? Any ideas? So let's say I ask, what color is an apple? You ask me, what color is an apple? And my response is, what color is an orange? And you say, well, that's not the answer. And I say, no, but it's the closest sentence in the embedding. You wanted the closest sentence. There's your closest sentence. You know what I mean? Like, so it's not the answer, right? And this may happen. I tried this again, and I put the capital of India is New Delhi, the capital of India is in the moon, the capital of India is in Asia, and the capital of Colombia is Bogota. There's similar sentences. Some of them true, some of them false, some of them true, but not the answer. And when I throw the question, it put it close to the capital of India is in Asia, which is, completely true, but doesn't answer my question. So how do we fix that? With re-rank. I'm not going to get very much into the re-rank, but this is something that you can try in the Cohere one. Imagine training a neural network with a bunch of questions and their answer, and a bunch of questions and the wrong answer. That's really close. And you train it to start picking up to start giving high scores to the answers and low scores to the non-answers. So you can say an apple, what color is an apple? An apple is red, and you put a high score. And then you say an apple is blue, and you put a low score. And Zoom is helping me here with the and if you train a neural network with that, believe it or not, it starts picking up what a right answer is and what a wrong answer is. With the same faith we have in neural networks that we can't fully explain, that's kind of how re-rank works. And finally, I'll tell you a bit about vector databases, and this is the last thing I'm going to talk about today. When you do semantic search, this can be pretty hard because it can be pretty slow, right? Like for every question, I have to look at the entire database, look at all the distances, all the similarities, compare them, organize them, take the smallest one. I can do that much faster with, if I have 1,000 documents, I have to look at 1,000 distances every time. Vector databases are pretty good for that because they, first of all, store your stuff really well. And second of all, they store a lot of, I'm not going to get too much into the details, but they store things into trees and do a lot of like smart things that when you search, it doesn't have to search the whole thing. It actually starts searching it faster. I can get into more, but I just want to throw them out there. This would be llama indexed, it would be LangChain, anything like that. And we covered a lot of stuff today, so I think I'm gonna say thank you so much. Before we get into questions, thanks to Mon and Syed for the invitation. This is really, really nice. I had a great time. You all answered my questions and asked a lot of really good ones. If you want to follow me, I have a YouTube channel. It's called Serrano Academy, and I got a lot of videos there. So you should check them out. In particular, this came out of 3 videos: attention mechanisms and transformer models. So you should check them out. And we made a course at Cohere called LLM University. So you should check it out. It's llm.university, where all this stuff appears. So anyway, I'm here for questions. I can stick around for as long as we want. So thank you. Thank you for the invitation. Thank you for your attention. I've had a wonderful time talking to you.
Wow, that was incredible. I didn't think the LLM this much be easier to understanding the architecture, understanding everything. So now I know many of you probably have burning questions, and I also have a lot of questions. So just open the floor for the question.
Yeah, perfect.
Let's see what question we have. What are the possible application of Gen AI in the healthcare sector?
Ooh, this is very good. Very good question. Yeah.
Yeah.
Actually, I was talking, I had a live session with Josh Starmer from StatQuest recently, and he talks a lot
Mhm.
about that stuff. So check out his channel because
Mhm.
he says it very much into science, genetics, and stuff. There's a lot they do, and I'm going to answer with my own little knowledge. But I mean,
Mhm.
languages are sequences, and sequences like genomics are also sequences. And there's a lot of sequences in science that can be studied in a very similar way using attention, using LLMs. So that definitely LLMs really really have a lot to add there. Others, I mean, I've seen a lot of chatbots that do RAG and that answer questions, medical questions, you know. So obviously they're not going to replace a doctor, but if you're going to wait 3 days to see a doctor and there's a chatbot that can do RAG and answer something, I've seen a lot of, like in a lot of hackathons, there's always a good project that does kind of like an LLM doctor with chat. So I think there's a lot of good applications, whether for the science and the medicine, and also for the serving people. So yeah, man, this is something that excites me a lot because it's a way, you know, it's a very an application.
I think there's so many open sources also coming. It's like the Mona AI, the amazing open source in the healthcare related to AI.
Yeah, very true.
So the another question is how to integrate AI with the agriculture for sustainable development.
Ooh, those are great questions.
Yeah.
AI. Very good question. I have seen. This is I would say probably more classical AI, like I mean image recognition. I've seen image recognition models that do like you know, they recognize the vegetable for like classifying it and making it quicker. I think a lot can be done, or also to like find regions to good places to plant and stuff like that. I don't know very much of that, but I've seen you can do a lot of study of the terrain and things like that. Yeah. Actually, something came to mind in the healthcare. Do you know the eye exam, right? That it was Google. It's big in India actually with the Google. There's an exam of the eye that if you have diabetes, you could go blind, and it's an exam that a doctor can do, and it's looking at the eye. It's looking at a picture of the eye, and then if you don't do it quickly, you may go blind. And I think Google and I think in India that this was done pretty, and it helped a lot of people because it was like an exam that they could use a CNN to tell if you needed to go to another more exams or if not. And then all of a sudden, not everybody had to go to a doctor because you would do this exam and it would just select the ones that needed the most. And it was very successful. So I've seen a lot of applications in healthcare. I've seen others that take a picture, for example, like a mole, and it helps you know if it could potentially be cancerous or something. So not LLMs, but like classical AI has done a lot in medicine. And I have no doubt it in agriculture as well. I don't unfortunately know that much of the applications, but I have no doubt that it's had good impact.
Make totally sense, yeah. So there's another questions. With the increasing capability of LLM, what ethical framework do you think should be implemented to ensure their responsible use in society?
Yeah, that's hard. That's a hard problem. Everybody's trying to figure it out. I think with everything, right? Like with everything, you cannot fully regulate it, right? Like cars, you can regulate cars, but somebody can just drive like insane, right? So they can make sure you don't do something twice, but for the first time, you can only put so many regulations. A lot of it is asked, especially because LLMs and there's a lot of plagiarism that is really hard to detect. There's a lot of malicious uses that are hard to detect. I would say the answer is I have no idea, and whoever's worrying about that, it has a big problem in their hands. I would say one thing to notice is that there are different levels of responsibility, right? Like you have I like to have this parallel, and here I have imagine that you have the electricity company, right? That provides electricity. They need to make sure it's not spiked or anything like that. Then you have the people building electrical things like an oven, and they have the people who use the oven, right? Here you have the model builders like Anthropic, LLM, Cohere, OpenAI, that build models. They want to make sure they're responsible. They want to make sure they are not biased, which is very hard because the data is biased. They make sure that they are not violent, that they don't speak violence, they like hate speech, everything like that. Then you have the people creating the apps using the models. Those are the ones that build the ovens, right? This is the electricity. They make sure that they also build applications that are responsible. that they don't add data, that they don't have malicious
Hmm.
goals, etc. And then you have the users. The users also have to make sure we do everything responsibly. So yeah, it's a very hard run.
Yeah, like the Shakespeare also said, there is nothing either good or bad, but thinking make it so. So totally agree. Yeah, it depends on
Exactly.
how you use.
Exactly. Like it's one more tool we use in society, and in the past we've noticed that everything can be used for evil.
Yep.
We just try to use it for good, but it's
Yes.
not easy. Yeah.
So we'll go for the second question. Considering the advancement in the deepfake technology for voice and video, what measure can be taken to detect and prevent the spread of misinformation while still promoting the innovation in AI? Oh,
So how do we promote? How do we make sure there's no spread of misinformation, right?
yeah.
Yeah. Excuse me.
Mm.
Actually recovering from COVID. I just had it for the second time, so it's coming back. So I'm coughing a little bit.
Mhm. Yeah.
Sorry.
No
Um,
worries.
yeah. Um, yeah. I mean, I think like as I said, these models are not built to say the right thing. They're built to say the most likely response.
Mhm.
So the internet is a bunch of garbage, right? So if you imitate
Yep.
the internet, it's bad. But
Mhm.
I think things like RAG are very useful, and tool usage is really useful. So once you integrate it with things, for example, if I ask it a math equation, if I ask it how much is 3 plus 5,
Mhm.
it's not going to answer from text. It pulls out the calculator
Yep.
because the calculator is always right.
Mhm.
If it says, a question that I can search in Wikipedia or something, like if you attach it, if you give it enough tools, it's good at following orders. That we know. And so if you give it enough tools, I think it can be as accurate as possible. So we for that we have ways. For things like biases, yeah, I mean it's introducing data that's not biased, but the data we have is built by humans, so therefore it's horribly biased, and even we have our own biases that we don't even know. So that's
Yes.
a problem about as difficult as removing bias in humans. So that's an uphill, that's an ongoing
Hmm.
battle, but it's basically doing everything you can to make the data as unbiased as possible.
Ah, cool. Yeah.
Yeah.
So there's another one. The Arman asked this one. How can we maintain same output from LLM, especially when we productionize LLM model? We are not getting the same LLM output
Yeah.
every time.
Yeah.
This
That's a good
crucial,
question.
especially for classification model. Output
That's a good
category will change
question.
from multiple lens. Yeah.
Oh, for classification, I would really hope is the same. That well, so here's the thing. I mean, we don't want it to always give the same answer when we ask the same question. If it's for playful, right? If it's for ChatGPT and you ask it, you want it to be a different answer. But at the same time, you want it to be right.
Yep.
So, you remember how like we turn the scores into probabilities, right?
Hmm.
So you can take scores and turn it into probabilities, but you
Hmm.
can also add something called temperature. Like I can, if I really like separate the scores more and turn to probabilities, I could be maybe not 60-40, but I can make them 99.9 and 0.01, right? Like I can make this much more drastic. Like I
Hmm.
can take the highest one and really make it higher, and the lowest one is really to reduce entropy, and that's called
Hmm.
temperature. So I have
Yeah.
whenever you look at an LLM, you have a little knob called temperature, and if you set
Hmm.
it on 0, it's
Hmm.
always going to respond the most likely thing. So it's always, I would, I think it will always respond the exact same thing to you, or very similar. Like it's not gonna
Hmm.
get creative. It's gonna answer the safest thing. And if you make it really high, it's gonna go unhinged. It's gonna, so if you want to say something really creative, you put the temperature
Hmm.
high. But if you want something for customer support, something that's
Hmm.
reliable, doesn't need to be imaginative, doesn't need to be fun, it just needs to be reliable, then you put the temperature low. So that's for
Hmm.
generation. For
Hmm.
classification, I think we just need to make better models, because if we're answering different things in classification, that's just a we need better better models.
Yeah, yeah, totally makes sense. So it's kind of we have to understand how the temperature will work. So understanding this
Exactly.
kind of problem. Totally
Exactly.
agree. Yeah. So there's another one. When people say GPT is built on billions of parameters, what are these parameters and how long does it take to build on and train on each parameter?
Great
I
question.
think
Great.
he want to build a chat GPT.
You want to build a chat GPT? That's awesome.
Yeah.
Yeah, I mean, the parameters are this, I mean, there's a
Mm-hmm.
lot of stuff. Let me see if I can pull out
Mm-hmm.
a model of, where did I have my, where did I have it? I talked a lot. Sorry. The parameters are basically here, right?
Hmm.
Like, you have a lot in the embedding. But the main thing is, imagine if you remove attention, then you have a neural network, right? With feed
Hmm.
forward, feed forward. So those are the parameters. That's the WhatsApp neural network that auto completes. And then
Mm-hmm.
attention, then you throw in a bunch of matrices, so key query value matrices. So in between every layer, you have a bunch of key query and value matrices, and
Mm-hmm.
that's and those are the parameters. And so there are lots and lots and lots of them. But mostly feed forward and attention matrices are where the parameters are.
Makes
Yeah.
sense. So this is the last question, and I ask so many times this question, and I am still not kind of understand how it will work. So what you say, because if I'm building some kind of generative AI product and it takes a
Yeah.
lot of GPT and a lot of energy and a lot of cost.
Yeah.
So in the future, is there any some things we can do using the super quantum computer, use Gen AI to increase the speed and
Ah.
reduce the cost, some kind of things? Because this way people are not gonna thinking. And if something is built on that kind of area and you have expertise, you can do something great.
Yeah. Yeah, that's a great idea. By the way, before I answer this, there's one extra one in the chat that I want to answer.
Yeah, yeah.
But yeah, that's a great question, and yes, you had a great answer there, Mon. The idea is that, I mean, I think when we do something, we have a huge neural network and it works,
Yep.
and then people are trying to make it smaller and smaller and smaller. So embeddings are already getting smaller and just as good. A lot of work is done into that, like reduce the neural network and try to make sure it works almost the same. Like if I reduce it by a half or a third and I make it 99.9 as good, that's good. So you can use classical methods to reduce dimensionality to get as small as possible. I still doubt they're gonna get too small because human knowledge is big and there's no way to get too small in that. But I think they'll be able to make it as dense as possible. And I do believe in quantum computing. For example, for generative models, I think quantum computers can be very useful there, because a quantum computer is pretty much a generator, right? Like a random number generator, right? A classical computer, no matter how big it is, it can't generate random numbers. It can't flip a coin.
Yep.
It can only do pseudo random number generation, right? Whereas a
Mm-hmm.
quantum computer, the 101 problem of quantum computers is flip a coin, right? Like when you measure a qubit, you're flipping a
Mm-hmm.
coin,
Yeah.
and that's purely random, like as random as the universe gets, And
Yep.
so when you do generation, you're generating random numbers. So any algorithm that generates random numbers or that generates any general algorithm, classical, has a bit of a problem generating the random number. You may not be getting it from the right distribution. You may not be sampling so easily, even though we have computers that are so big that they this doesn't become a huge problem. But quantum computers, they don't have a problem. They generate very easily. Even if you don't want
Mm-hmm.
it to generate random stuff, they still generate random stuff.
Yeah.
So we have a hope that I have a hope that quantum computers, when they're big enough, generative modeling is what they're gonna be the strongest at, even more than supervised. I feel like classical computers are better supervised learning machines because they're more deterministic. But I feel like generative, I could be wrong, but I think generative AI
Mm-hmm.
will be strongly benefited by quantum computers.
Hmm.
Yeah, we'll
Sounds
see, right?
perfect. Yeah.
Put in my
Yeah.
words, but yeah.
Yeah. So I think all right, folks. I think
There's
we
a
have
question.
officially. Yeah. Hey,
Sorry,
go.
go ahead.
Yeah. Is there any questions, or are we gonna end this session?
There's one by George. Says, what's the likelihood for human extinction due to AGI? The Terminator thing.
Mm-hmm. Yeah.
And I answer philosophically, and I say that could be. I don't think
Okay.
it's unlikely that a computer can figure out that the best way to
Mhm.
preserve itself or the planet is to get rid of us.
Yeah.
I think humans are gonna do that way before. I think humans with machines at their
Mhm.
disposal are very much more dangerous than a machine by
Agree.
itself. So I think we won't give them the chance.
I agree.
Yeah,
So I think
yeah.
we'll come to the end of the session. So all right, folks, I think we officially banned Luis Brands of all its AI secret. A massive thank you for Luis, so generous sharing his
Thank you,
time and expertise,
thank you.
and to Arman for making this session possible. Remember, the only silly question is the one you don't ask.
I
Keep the
agree.
curiosity burning, and we can't wait to see you at our next Codecrafter adventure. Good night and happy coding.
Thank you for having me. Thanks for everybody.
Yeah, it's great to honor you.
Thank you.
Okay, guys.
Yes, sir. Thanks for joining.
Thank you. Bye bye.
Yeah.